All right, so section 3.5 is entitled rational functions. Good place to start is to define what a rational function is. And this is the opening of section 3.5. A rational function, ladies and gentlemen, is a function where we have a polynomial over a polynomial. So a rational function, again, is a ratio of two polynomials. Here are some examples of rational functions. The simplest of which would be f of x equals 1 over x, which is sometimes referred to as a reciprocal function, but it is a rational function. And notice the domain of 1 over x is going to be all real numbers except 0. Why can 0 not be found in the domain of this rational function, 1 over x? Well, by reason of the fact that we can never divide by 0. Anything divided by 0 is undefined. So this rational function is not defined at x equals 0. And so therefore its domain, which is represented using set or interval notation, excludes 0. G of x is another example of a rational function. Notice when you factor the denominator, it does factor in the product of two binomials. And then we have to ensure that we do not ever put any value in for x into this function for which it is undefined. Because of that, if you take 2x minus 3 and x plus 4 and set them equal to 0, you'll discover that 3 halves and negative 4 must be excluded from the domain of this rational function if it is to remain defined. So as long as you put any other real number in other than 3 halves or negative 4, the function will be defined. But if you try to evaluate the function at those two values there, 1.5 and negative 4, the function will be undefined. Last rational function, k of x, notice its denominator is x squared plus 4. And again, our concern is always with the denominator. We don't care if the numerator becomes 0. We are concerned whenever the denominator becomes 0. Well, guess what? X squared plus 4 will never be equal to 0 for any value of x. Reason being is because you can never square a real number and get negative 4. So this denominator never will be 0. And for that reason, the domain for this rational function is all real numbers. In other words, it is defined for all real numbers. Okay. Any questions about the domains of those rational functions here? So it's when the denominator is 0 that a rational function is undefined. All right, now, in order to ultimately be able to analyze and graph a rational function, we need to mosey on up to this notation. When we see this x with this arrow pointing to this little c with a plus sign, we are to interpret this as saying that x is approaching some real number c from the right of c. Okay, so we're on the x-axis and we're moving in towards some real number c on the x-axis, but we're moving in from the right of that real number c. That's what that little plus sign means. We're moving in from the positive side of that real number c, or moving in from the right. This notation is indicating if we're on the x-axis and moving towards some real number from the left of that real number. So we're approaching the real number from the left on the x-axis. That's what that little negative sign indicates here. Next notation is x approaches positive infinity. It means we go far to the right on the x-axis, or x approaches negative infinity, which means we venture far to the left on the x-axis. Let's take a look at the graph of f of x equals 1 over x. You can see that it has been graphed in blue here. We're going to look at the behavior of this graph as far as its relationship is with the x-axis and the y-axis. Notice as I go far to the left on the x-axis, in other words, as x approaches negative infinity, the y values on this graph are actually approaching 0. And they're actually approaching 0 from below 0. In other words, this graph is approaching the x-axis from below the x-axis, not from above, as x approaches negative infinity. For that reason, technically, we really should use a little minus sign up here on the 0. That indicates that y is approaching 0 from the left, or excuse me, from below 0. That is indicating that y is approaching 0 from below. All right. If we go far to the right on the x-axis, in other words, as x approaches positive infinity, we can see that our graph is diving down towards the x-axis. In other words, the y-coordinates of this graph are again approaching zero, but they're approaching zero from above zero. And so technically, and I'm surprised your author hasn't included these little signs in here, but y should be approaching zero from above. So we'll put a little plus sign here. That means y is approaching zero from above. The little negative sign up here means y is approaching zero from below. Interesting thing occurs as we near the y-axis, as x approaches zero from the left. In other words, we're on the x-axis and we're moving towards the origin, albeit from the left of the origin. So as x approaches zero from the left, that's what this notation is saying. X approaches zero with a little negative sign. That means x approaches zero from the left. As we are approaching the origin from the left on the x-axis, our function is diving down towards negative infinity. In other words, y we say is approaching negative infinity. Let's go on the other side of the y-axis. Suppose that we allow x to approach zero from the right of zero, meaning that we're moving in towards the origin on the x-axis from the right, not from the left. If that's the case, our function is blowing up towards positive infinity. It's going up forever. And that's what this notation is indicating right here. These tables are just giving us some specific ordered pairs or points that lie on the graph for these extreme cases. For instance, this first table up here says that as x approaches negative infinity, as we go far to the left on the x-axis, far out here to the left on the x-axis, f of x is approaching zero from below. So you can see that the value of f of x is getting closer and closer to zero, albeit from the negative side of zero. Okay. Okay, and let's look at this table here, down here. This is saying as x approaches positive infinity, we go far to the right on the x-axis, f of x is approaching zero, but approaching zero from the positive side of zero, meaning approaching zero from above. This table down here is saying that as x approaches zero from the left of zero, meaning from the negative side of zero, the function is diving down towards negative infinity here, going down to negative infinity. And finally, this table up here is saying as x approaches zero from the right, the function is blowing up to positive infinity. Any questions about the analysis of this rational function f of x equals 1 over x? And the notation that's being used. Okay. All right, let's move on now. Okay, so let's look at the graph of this rational function f of x equals 1 over x squared. And you can see that it has been graphed. There it is in blue. We can see that this graph is symmetric with respect to the y-axis, so this would be an even function. Do you remember the definition of an even function that I laid out several weeks ago? An even function is any function f of x, when evaluated at negative x, you get back the original function f of x. And you could see that that clearly would be the case here. If you put negative x in for x, you're still going to walk out with 1 over x squared after simplifying. That indicates that this is an even function, therefore its graph is symmetric with respect to the y-axis. All right, let's analyze it. As x approaches negative infinity, as I go far to the left on the x-axis, what's happening to the value of f of x? F of x is approaching what? Well, the graph is diving down towards the x-axis, meaning f of x is approaching zero. Is it approaching zero from above or from below? Above or from below? F of x is approaching zero from the positive side of zero, from above. Okay, so we should put a little plus sign there. As x approaches zero from the left, in other words, if we're on the x-axis and we're moving towards the origin, albeit from the left of the origin, the graph is blowing up to positive infinity. Okay, so f of x is approaching positive infinity. All right, I'm having a little problem with this mouse here. I've been having a little problem with it. But this should be positive infinity here, okay? Positive infinity. As x approaches 0 from the right, as we're on the x-axis, we're moving towards the origin from the right of the origin. Again, the graph is blowing up towards positive infinity. So again, this should also be positive infinity. As x approaches positive infinity, we go far to the right on the x-axis. What's happening to our function? Our function's diving down again towards the x-axis, meaning its y-coordinates are again approaching 0, but approaching 0 from above 0. Any questions about that there? All right. Okay. There we go. This is example 1 in section 3.5. It's all laid out here. Notice the notation is indicating the behavior of the graph the way I explained it. All right, ladies and gentlemen, for classwork number 1, I want you guys to fill in these blanks here. As x approaches these values for this rational function, whose graph is given right here, I want you to indicate what f of x is approaching. So do A through D for classwork number 1. A through D. All right. As x approaches negative infinity, we go far to the left on the x-axis. It looks like our graph is moving up towards the x-axis. In other words, f of x is approaching 0, or the y-coordinates on this graph are approaching 0, but approaching 0 from the negative side of 0, from below 0. Okay. As x approaches 2 from the left, that's what B is saying. So as we're on the x-axis, moving towards positive 2 from the left of positive 2, okay, our graph is diving down to negative infinity down here. So this should be negative infinity. As x is approaching positive 2 from the right of positive 2, that's what C is saying. So we're on the x-axis, moving towards positive 2 from the right of positive 2. Our graph is going up towards positive infinity. Oops, hold on a second. What just happened there? Okay. All right, so as x approaches positive 2 from the right, f of x is approaching positive infinity here. So positive infinity. So this should be positive infinity here. As x approaches positive infinity, we go far to the right on the x-axis. Our graph is diving down towards the x-axis, or its y-coordinates are approaching zero, but approaching zero not from below, but from above. Any questions about any of those? That's classwork number 1. All right, now we're going to define what a vertical asymptote is. All right. We say that a vertical line represented by this vertical red dashed line is a vertical asymptote to the graph of a rational function if any one of these characteristics is true. In other words, as x approaches that real number c on the x-axis from the left of c, if our function goes up towards positive infinity, or as x approaches c from the left, our graph dives down to negative infinity, or as x approaches c from the right, the graph goes up to positive infinity, or as x approaches positive c from the right, the graph dives down to negative infinity. We would classify this vertical red dashed line as being a vertical asymptote. Ladies and gentlemen, notice the graph will never touch or cross a vertical asymptote. And the reason why that is because at vertical asymptotes, your rational function is undefined. And so that gives us a little inkling as to how we're going to find vertical asymptotes. That gives you a hint of something to come. Okay. All right, so that's what a vertical asymptote is. How do we find vertical asymptotes? Well, we find vertical asymptotes by setting the denominator of a rational function equal to 0 and then solving the equation. That's how we locate where vertical asymptotes hang out. Because it's at vertical asymptotes that rational functions are undefined. Okay. So that's why the graph of a rational function will never touch or cross a vertical asymptote anywhere. Here are some rational functions. We're going to identify where their vertical asymptotes hang out. The first one is f of x equals 2 over x minus 3. In order to determine where its vertical asymptote lives, we take x minus 3 and set it equal to 0 and then solve for x. When you take x minus 3 and set it equal to 0, you'll discover that you get x equals 3. It's at x equals 3 where f of x in a is undefined. And for that reason, that's where its vertical asymptote will occur, is at x equals 3. Notice the graph of f of x never touches or never crosses that vertical asymptote. It cannot, because you cannot have any point on the graph that has an x coordinate of 3, because at x equals 3, f of x, this rational function, is undefined because you're dividing by 0. The second rational function, g of x, to discover where its vertical asymptotes occur, we would like to take this denominator, which is a trinomial, and completely factor this. And your author has done that. Your author has completely factored 3x squared plus 5x minus 2. And notice it factors into these two binomials, of which if you were to set equal to 0 and then solve for x, you would discover that you have two vertical asymptotes. One that occurs at positive 1/3 and the other one that occurs at negative 2. It's at these values where your function is undefined. And for that reason, the graph in blue for this rational function never touches any one of these vertical red dashed vertical asymptotes. Is this making sense how we're locating vertical asymptotes for a rational function? The last one is 4x squared over x squared plus 4. To see if it has any vertical asymptotes, we set the denominator x squared plus 4 equal to 0. And then we try to solve for x. But the problem is when you try to solve that equation for x, you do not get real solutions. Meaning, ladies and gentlemen, there are no vertical asymptotes for this rational function k of x. And because of that, you can see that the graph never does approach infinity or negative infinity as x approaches any specific value on the x-axis, because there are no vertical asymptotes for that one. Any questions how to locate vertical asymptotes for these rational functions here? It's the denominator you set equal to 0 to locate them. Okay, because when the denominator is 0, that's where your rational function is undefined. All right, here is classwork number 2. Given these 3 rational functions, I want you to identify where their vertical asymptotes occur. Please do indicate the equation of the vertical asymptote, if they do have one, by using x equal to whatever number it is. So we'll call this classwork number 2, A through C. All right, for the first one, A here, to determine where a vertical asymptote hangs out, we would set x plus 1, the denominator, equal to 0, and solve for x, and you discover its vertical asymptote hangs out at x equals -1. So it only has one vertical asymptote at x equals -1. The second one, we would have to set the denominator equal to 0, which means we have to solve a quadratic equation, which I chose the factoring method to do so, factored that difficult trinomial. Setting both factors equal to 0, solving for x, I discover I have 2 vertical asymptotes. One at x equals 5/2 or 2.5, and another one that occurs at x equals -2. Finally, the third rational function, m of x down here, if you set its denominator equal to 0, you'll discover that it does not have any vertical asymptotes, as the denominator never will ever be equal to 0 for any value of x. So there is no vertical asymptote for m of x. Any questions about locating the vertical asymptotes of these rational functions? Any questions? Okay. Now, all of these rational functions up to this point have never had duplicate factors in the numerator with any factors in the denominator. What happens if you do? For instance, look at this rational function here. And for this reason, ladies and gentlemen, you might want to remember, if you can factor your numerator of a rational function, please do so, and make sure you completely factor your denominator also. Reason being is because you can see that after factoring this numerator here, we do have a duplicate binomial in the numerator and the denominator of this rational function. So this x plus 1 being a common binomial factor between the top and bottom would actually reduce out or cancel out to 1. So if you did not factor this numerator, okay, and you looked at this rational expression, you might falsely be led into believing, oh, I have a vertical asymptote at x equals -1 after setting the denominator equal to 0 and solving for x. But as it turns out, we do not have a vertical asymptote at -1. In fact, what we have, ladies and gentlemen, because x plus 1 drops out with the factor of x plus 1 in the numerator, we have what is called a hole that occurs in the graph at x equals -1, not a vertical asymptote. All right, and that where that hole occurs can be found by putting -1 into your original function, putting -1 in wherever you see x here. Okay, or I should say, you put -1 into the function after you reduce out or cancel out the x plus 1s here. So this -1 should go right in here for x. And we discover that our hole in our graph occurs at the ordered pair of -1. And if you put -1 in here, 2 times -1 is -2 plus 3 is 1. So the hole occurs in the graph at -1, 1. There's a huge difference between a hole and a vertical asymptote. Okay. Don't get me wrong, the function is still undefined at x equals -1. That's why there is no point on the graph that has an x coordinate of -1, but it's just a hole. The graph is not approaching positive or negative infinity along this vertical line x equals -1. So it's not a vertical asymptote here. It's just a hole. And so again, make sure when you have a rational function, you always factor your numerator completely and your denominator. And if any factors drop out between the top and the bottom, that's where you're going to locate where you have a hole in your graph, as opposed to when you have where you have a vertical asymptote. We've never had that problem with any of the other functions up to this point. So this is an important case here to just keep in mind when working with rational functions, that sometimes you may not have a vertical asymptote for a factor in the denominator, but you may have a hole that occurs there if that factor drops out with a like factor in the numerator. Any questions about this whole business here? Okay. All right, now horizontal asymptotes. Ladies and gentlemen, what is a horizontal asymptote? We've seen that vertical asymptotes occur where a rational function is undefined, and the graph of a rational function will never touch or cross a vertical asymptote. But what's a horizontal asymptote? Well, a horizontal asymptote is a horizontal line depicted as this red dashed line, such that the graph will either approach it from above or below as x approaches either positive infinity or negative infinity. So the nature of a horizontal asymptote is not realized until x becomes very large or very small. So if we go far to the left on the x-axis and the graph approaches that horizontal red dashed line from above or from below, then we say that this horizontal line is a horizontal asymptote. Or if we allow x to approach positive infinity, we go far to the right on the x-axis, and our graph is approaching that horizontal line either from above or from below, we say that we have a horizontal asymptote. Now, can a horizontal asymptote cross or touch a can a rational function's graph cross or touch a horizontal asymptote? Well, unlike a vertical asymptote, the answer is yes. A graph of a rational function can cross or touch a horizontal asymptote. Here's an example right here where the graph actually crosses the horizontal asymptote. Okay, right here. But then the key is, and the nature of a horizontal asymptote, again, is only realized for very large or small values of x. So despite this graph crossing through the horizontal asymptote right here, you can rest assured that as x approaches positive infinity, the graph then must eventually become asymptotic with respect to that horizontal line, never to cross or touch it ever again. So yes, a graph can cross or touch a horizontal asymptote. All right, how do we, find out where the horizontal asymptotes are for a rational function? We see now to find where vertical asymptotes are. They occur where a function is undefined, and by setting its denominator equal to 0, that helped us locate where the vertical asymptotes are. Well, how do we determine if a rational function has a horizontal asymptote, and what would be its equation? Well, all we got to do is compare the degree of the numerator to the degree of the denominator polynomial in a rational function. You're going to have three possible scenarios. Scenario number one, if the numerator degree is greater than the denominator degree, in other words, if this degree here is greater than this degree here, then we would say there would be no horizontal asymptote for such a rational function. None. Scenario number two, if the numerator degree is less than the denominator degree, then we would say that the horizontal asymptote is the x-axis, whose equation is y equal to 0. That would be the horizontal asymptote. If the degree of the numerator is equal to the degree of the denominator, then we would say we do have a horizontal asymptote, and its equation would be y equal to the ratio of the leading coefficients of the numerator and denominator polynomial. Okay, so this would be the equation of your horizontal asymptote if the numerator and denominator degrees are equal to each other. All right. This is just going into a greater depth analysis of what that above was just saying. For instance, if the numerator degree is greater than the denominator degree, here's an example. If we have like a fourth degree polynomial over a second degree polynomial, for large values or small values of x, this polynomial's behavior will ultimately settle down into the behavior of x to the fourth divided by x squared, which is to say y equals x squared. Well, remember that leading term theorem we looked at several weeks ago. If we have an even degree polynomial with a positive leading coefficient, or a negative leading coefficient for that matter, the graph will be going upwards to the left and right or downwards to the left and right, in which case there is no horizontal asymptote, because as x becomes small or large, this graph never does settle down towards a horizontal line. So you can see why such a function would not have a horizontal asymptote in that situation. If, on the other hand, the degree of the numerator is less than the degree of the denominator, you can see for this example of f of x equals x squared over x to the fourth, for large or small values of x, this function would be really equivalent to 1 over x squared. And you can see that clearly as x approaches negative infinity or positive infinity, the graph is diving down from above towards the x-axis. So the x-axis, or y equals 0, would be the horizontal asymptote in that scenario there. Finally, if the degrees of the numerator and denominator polynomials are equivalent to each other, essentially the x squareds would drop out and would be left with f of x is equal to 4/3. So the equation of the horizontal asymptote in this scenario would be y equal to 4/3. Okay. All right. Example 3 walks us through 3 rational functions and how to determine their horizontal asymptotes. The first function a here, the degree of the numerator is less than the degree of the denominator. Therefore, by the theorem mentioned above, that being the case, the horizontal asymptote would have to be the x-axis. Y equals 0 would be its equation. And you can see after graphing this function f of x and a, you can clearly see that, yes, it does appear that the graph is asymptotic with respect to y equals 0 or the x-axis. For a rational function g of x and b, you can see the numerator degree exceeds the denominator degree. In that case, there would be no horizontal asymptote, according to our theorem above. And you can clearly see that after graphing g of x, there is no horizontal asymptote. As x gets large or x gets very small, the graph never does settle down towards any horizontal line. No horizontal asymptote. Finally, for the last function, h of x, where the degree of the numerator is equal to the degree of the denominator, being both second-degree polynomials, the horizontal asymptote would be y equal to the ratio of 8 over 2. So the horizontal line, y equals 8 halves or y equals 4, would be the horizontal asymptote. And you can see the graph does, in fact, become asymptotic with respect to that horizontal line there. And then, ladies and gentlemen, you're probably wondering, how would you determine where this graph crosses the horizontal asymptote? I will show you in an example coming right up how we can determine this point of intersection between the graph and this horizontal asymptote. Remember, I indicated a graph can cross or touch a horizontal asymptote, but it can never cross or touch a vertical asymptote. All right, classwork number 3. Here are 3 rational functions. I want you to determine what the horizontal asymptotes would be, if the function even has one. So we'll call this classwork number 3.
Fucking went straight over mine.
All right, for A here, f of x, notice the degree of the numerator and denominator polynomials are equivalent. They're both second-degree polynomials. Therefore, the equation of the horizontal asymptote is going to be y equal to the ratio of the leading coefficients. Y is equal to 7/4. That horizontal line would be the horizontal asymptote. Or you could turn this into a mixed number for plotting purposes. It would be 1 3/4. Y is equal to 1 3/4. Second one, m of x, the degree of the numerator is greater than the degree of the denominator, and so there would be no horizontal asymptote for this rational function. Third one, the degree of the numerator is of 0 degree. The denominator is a second degree polynomial. Because the numerator degree is less than the denominator degree, the horizontal asymptote is going to be the x-axis, whose equation is y equals 0. That is the x-axis. All right, is this making sense how we're locating horizontal asymptotes for rational functions here? Horizontal asymptotes, there's the answers right there. All right. Now, ladies and gentlemen, we're going to revert back to the last example, function C here, h of x, which was the second degree polynomial over the second degree polynomial. And we indicated that its horizontal asymptote would be y equal to 8/2 or y equals 4. The question is, where does our rational functions graph cross or touch that horizontal asymptote? The answer lies in example 4. Your author indicates where the graph of h of x, this rational function, crosses the horizontal asymptote and how to find it. How to find it? We set y equal to 4 because that is the equation of our horizontal asymptote. It's y equals 4. So we set h of x, or this function, equal to 4. And they've done that right here. And now we have to solve this equation for x. To do so, they multiply both sides of the equation by 2x squared plus 1 to get rid of the fraction on the left side. Notice that the 2x squared plus 1s will cancel out or cross reduce out, leaving you with 8x squared plus 9x minus 5 equal to, you got to multiply the right side by 2x squared plus 1 now, equal to this. Notice when we subtract 8x squared from both sides of our equation, the 8x squared drops out on both sides of our equation. How nice is that? So our quadratic equation immediately collapses down to an ordinary linear or first degree equation, of which the solution would be 1. So you can see that, yes, the graph of this rational function h of x will cross the horizontal asymptote y equals 4 at x equals 1. To find the y coordinate of that point of intersection, you put 1 back into the original function. So you'd have to evaluate h at 1. So you'd put 1 back into the original function here. So h of 1. After you put 1 in for x here and here and here, you would discover you get 4. So it's at the point 1, 4. That is the point of intersection between the graph of this rational function and its horizontal asymptote. Any questions how we found that point of intersection between the graph of the rational function and its horizontal asymptote?
What do you plug 1 into again?
The original function. You got to go back up here to h of x and put 1 in for x wherever you see it in its definition.
In the numerator and the
Yeah, oh yeah, everywhere. So 1 has to go in here, 1 has to go in here, 1 has to go in here for x. Okay, so you're going to have 8 times 1 squared plus 9 times 1 minus 5. That's going to give us what? 12 for the numerator. And then you put 1 in for the denominator. 2 times 1 squared is 2 plus 1 is what? 3. 12 divided by 3, you got it, is equal to 4. So that's the y coordinate of this point of intersection between the graph and the horizontal asymptote, 1, 4. Are we seeing how we found that point of intersection here? As laid out as example 4 here. All right, so these examples in this textbook are very instructive and basically walk you right through the entire topic of the entire section. That's why I hope if you haven't looked at these examples in the past that you will start to do so. It's a great way to supplement what's being said in class here. All right, ladies and gentlemen, there is another type of asymptote that a rational function could possess from time to time. It's called a slant asymptote, okay? And how do we know if a rational function's graph possesses a slant asymptote? Well, this is how we know. If the degree of the numerator polynomial is precisely 1 larger than the degree of the denominator polynomial, then your rational function will have a slant asymptote, of which the graph will approach when x gets very large or very small. All right. The graph will get infinitesimally close to a slant asymptote as it does a vertical asymptote, but will never ever touch or cross it anywhere. So that's how you know if a rational function has a slant asymptote. That is again determined if the degree of the numerator is exactly 1 greater than the degree of the denominator. Well, that's great. But how would we actually determine where the slant asymptote is, or more specifically, what its equation would be? Well, to determine that, ladies and gentlemen, we would have to literally divide the denominator of the rational function into the numerator. And so we may have to either resort to long polynomial division, or maybe we can undertake the task by using the synthetic division that we looked at in the past.
Would you mind going up back to the one you just solved for just 1 second? I just want to take a picture of it.
Well, this is in your textbook. It's example 4. It's all laid out there. Page 352.
All right, thanks.
Yeah. So if I take x minus 1 and divide it into x squared plus 1, your author chose to use long polynomial division to do so. You can see that the equation for the slant asymptote is going to be y equal to x plus 1. You're probably wondering, what do we do with the remainder here? What do we do with that? Well, when it comes to a slant asymptote, we don't really care about the remainder portion of the quotient. And the reason why we don't care about the remainder portion of the quotient is because of this. Because, ladies and gentlemen, as x becomes very large, or as x becomes very small, doesn't matter in both cases, you know what's going to happen to 2 over x minus 1? It's going to get closer and closer to what value? What do you think? Look what happens to this fraction when its denominator gets larger. What is the fraction really approaching or getting closer to? What are these values getting closer to? They're approaching what value?
0.
0. So as x gets very large or very small, this remainder portion of our quotient is going to approach 0 anyways. For that reason, we don't care about the remainder portion. The equation of the slant asymptote for this rational function is y equals x plus 1. That is it. That is its equation. And therefore, we can graph that. Being in slope-intercept form, that shouldn't be too difficult to graph. And you can see that the graph of y equals x plus 1 is indeed this slanted red dashed line. That is the slant asymptote for this graph. Notice, because the numerator is of degree 1 larger than the denominator, there is no horizontal asymptote. So a rational function can never possess both a slant asymptote and a horizontal asymptote. That can never happen. The vertical asymptote, notice, is x equals x equal to positive 1. Why is that? Because at x equals positive 1, our denominator is 0, and the function is undefined at positive 1. That's your vertical asymptote. Pretty cool, huh? See how that works there? All right, so again, the degree of the numerator has to be precisely 1 larger than the degree of the denominator, even to have a slant asymptote. If that's not the case, then you don't have a slant asymptote. All right. Okay. Here's another example. This is example 5 in your textbook again. We have a second-degree polynomial in the numerator over a first-degree polynomial in the denominator. Because the degree of the numerator is exactly 1 larger than the degree of the denominator, there will not be any horizontal asymptote, but there will be a slant asymptote. In order to find its equation, your author chose to use long polynomial division and divide x minus 2 into the numerator. And there it is, all laid out, the long polynomial division. And notice the equation of the slant asymptote is going to be y equal to 2x minus 1. We don't care about any remainder portion, because that just basically, the remainder drops out to 0 anyways as x becomes large or small. You can see that they did graph y equals 2x minus 1. There it is. That slanted dashed red line. And you can see that the graph is indeed asymptotic with respect to it as x approaches negative infinity or as x approaches positive infinity. And notice there's also a vertical asymptote for this rational function, which would be what? Would be x equals 2, correct? Notice because x minus 2 does not cancel out with any factor in the numerator, we do have a vertical asymptote at x equals 2. If I was to have a hole in my graph at x equals 2, what would have to happen to the factor of x minus 2? If I was to have a hole in my graph at x equals 2, what would have to happen to the factor of x minus 2 if that was to be the case? It would have to what? It would literally have to cancel out with an x minus 2 in the numerator, but because it doesn't cancel out and it remains as is, we have a vertical asymptote at x equals 2. Okay. Sometimes using our transformations that we used in the past on functions, it can aid our ability to sketch the graph of a rational function. Notice for this complicated rational function here, the parent function would be y equals to 1 over x squared. And the graph of y equals 1 over x squared is this graph that's represented in gray here. You see the graph here, gray. Notice that the horizontal asymptote is y equals 0, which is the x-axis. And notice 1 over x squared as a vertical asymptote, which happens to be the y-axis, whose equation is x equals 0. Because it's at x equals 0, this function is undefined. So I have a question. If I go from 1 over x squared to this complicated rational function, what kind of transformations would the graph of the parent function undergo? Do you remember the order in which we took those transformations? First, we deal with any sort of horizontal translation. And notice because we got x plus 2 here, that means the graph of 1 over x squared would be shifted 2 units to the left. Notice there's no horizontal compressions or shrinking or vertical compressions or shrinkings because the function is being multiplied by 1 and x is being multiplied by 1. So there's no non-rigid transformations that are occurring. Notice there is no reflections about any axis because we don't have a negative sign in front of our function and we don't have a negative sign in front of x. So the graph is not reflected about the x or the y-axis. Finally, we are adding 3 to the overall function, which means that our graph would be translated upwards 3 units. So you can see the gray graph upon being shifted 2 units to the left would become the blue graph. And then the graph being shifted upwards 3 units would become the green graph. And so the green graph is the graph of this rational function right there. Notice the horizontal asymptote, which used to be y equals 0, the x-axis, is shifted upwards and now becomes the horizontal line y equals 3. Any questions how using our transformations we studied in the past enable us to take the graph of 1 over x squared and then shift it around to get the graph of this more complicated rational function. All right. Okay, so in general, this is what you want to be conscious of when you're being asked to graph a rational function. You want to consider finding these things for the rational function because they will all aid your ability to accurately represent its graph. Number one, you want to try to find any y-intercept that the rational function may have by letting x be 0. Number two, you might want to try to find any x-intercepts that the rational function has by setting y or f of x or the function equal to 0 and then solving for x. Number three, you want to identify if there's any vertical asymptotes that the rational function has. And if it does have any vertical asymptotes, very important to graph them as vertical dashed lines in the xy plane. Fourthly, you want to determine whether the function has any horizontal asymptotes or any slant asymptotes or neither. And if they do, you also want to graph them using dashed lines in the xy plane. If your function has a horizontal or slant asymptote, you want to determine where the graph of the rational function crosses or touches the horizontal or slant asymptote. If it doesn't have a horizontal or slant asymptote, don't worry about number 5. Using the knowledge of whether the function is even or odd can aid your ability to sketch the graph accurately as far as its relationship with symmetry is concerned with respect to the x or the y-axis. And last but not least, later on, we may have to plot some other strategic points of the rational function to more accurately determine its graph. So what I'm going to do is I'm going to wrap this section up by graphing a couple of rational functions. And by going through these, hopefully you can see the analysis that we should pour into these things in order to succeed at graphing these things without a graphing calculator. Okay. So I am going to try to graph f of x equal to x plus 3 over x minus 2. All right. So I'm going to try to graph this here. Step number 1, we want to try to find any y-intercepts according to that table we just looked at. To find a y-intercept, we always set x equal to 0. So my y-intercept is going to be f of 0, which means I replace x throughout with 0. Looks like I do have a y-intercept, which is negative 3.5, which is negative 1.5. So my y-intercept is going to be 0, negative 1.5. That's my y-intercept. Number 2, any x-intercepts. To find them, we let f of x or y be equal to what? 0. Which means that I'm going to have to set this rational function equal to 0 and then solve for x. So now I must solve this equation for x to find any x-intercepts. To do so, I'm going to get rid of this fraction on the left side by multiplying the left side by x minus 2. But if I multiply the left side by x minus 2, I must multiply the right side by x minus 2. These x minus 2's drop out on the left, leaving me with x plus 3. The right is still 0. Now we simply solve for x and we get x equals negative 3. So we do have an x-intercept, one of them. It would be the point negative 3, 0. That's your x-intercept. All right. Thirdly, any vertical asymptotes. To find vertical asymptotes, I'm going to abbreviate as VA. I would literally set my denominator of my rational function equal to 0. Notice I don't have a hole at x equals 2 because this factor does not cancel out with 1 in the numerator. I will have a vertical asymptote. And its equation is x equals 2. That is my vertical asymptote. Number 4, do I have a horizontal asymptote? To find a horizontal asymptote, we would have to use that theorem that gave us our 3 possible scenarios. Notice the degree of the numerator polynomial is equal to the degree of the denominator polynomial. They're both first degree polynomials. Since the degree of the numerator is equal to that of the denominator, my equation of my horizontal asymptote is going to be y equal to the ratio of the leading coefficients of both polynomials. So y is going to be equal to 1 over 1, or 1. That is your horizontal asymptotes equation, y equals 1. Number 5, will my graph cross or touch the horizontal asymptote? To determine whether it crosses or touches the horizontal asymptote, let's take f of x, which is y, and set it equal to 1, which means I got to set my rational function equal to 1 and now try to solve for x. Multiplying both sides by x minus 2. When you multiply the fraction on the left by x minus 2, the x minus 2's cross cancel out, leaving you with x plus 3. Multiplying 1 on the right by x minus 2, we're left with x minus 2. Now we'll try to solve for x. To solve for x, I subtract x from both sides and discover something. My x drops out on both sides, and I'm left with a false numeric statement. And because I'm left with a false numeric statement, I would conclude that no, my graph will never cross or touch the horizontal asymptote anywhere. So graph of f of x never crosses or touches the horizontal asymptote. It'll never cross or touch the horizontal asymptote. All right, ladies and gentlemen, I think we're in a catbird seat now to graphing this rational function. We know a lot about it, okay? So we're now going to plot all this information we know about it in the XY plane and start to put together this graph.
So for the last one you just did, if the x's didn't cross out, then that means that they would cross or
Yeah,
touch.
if you get a solution to this equation, when you set your function equal to the horizontal asymptotic value, if you get a solution, that means the graph will cross the horizontal asymptote at that value. Okay, but I did not get a solution when I tried to solve this equation. No solution.
Mm-hmm. And do you always set it equal to 1 to figure this out?
No, you always set it equal to whatever y is equal to for your horizontal asymptote. It just so happens y is equal to 1. So I set my rational function equal to 1. If my horizontal asymptote was y equals 0, you would set this equal to 0. If the horizontal asymptote equation was y equals 5, I would set this equal to 5. Does that make sense? Okay, you always set it equal to what y is equal to in your equation of your horizontal asymptote. Okay. All right. Now here we go. We're going to try to sketch the graph of this function. Of course, graphing paper would be nice, but I'm just going to, sketch it. So I think we'll get the idea what's going on here. I'm going to plot everything I know. What do I know? I know my y-intercept is -1.5. Let's plot that point. There's -1.5 right there. There's my y-intercept. My x-intercept turned out to be what? -3,0. Plot that point. -3 zeros right there. There's my x-intercept. What else do we know? We know we have a vertical asymptote at x equals 2. Let's go ahead and represent it in our xy plane. So at +2, there's 1, there's 2. I have a vertical asymptote going right through here. There's my vertical asymptote at x equals 2. Make sure it's a dashed line. All right, anything else? Yes, I have a horizontal asymptote at y equals 1. Make sure we plot this as a horizontal dashed line. Y equals 1. So y equals 1. 1 is right here. So we put a horizontal dashed line right through the y-axis at 1. This is your horizontal asymptote. That's your horizontal asymptote. All right. Does my graph cross the horizontal asymptote? The answer is no. It never crosses or touches it anywhere. Because my graph will never cross or touch the horizontal asymptote, I can begin to sketch this graph. Let's go over here. Notice my graph has got to have an x-intercept of -3 and its y-intercept is -1.5. And my graph for x approaching -infinity has to become asymptotic with respect to this horizontal asymptote. So I think it's safe to say, ladies and gentlemen, that my graph has to go like this. And then my graph has to be asymptotic with respect to the vertical asymptote as x approaches 2 from the left. So as x approaches 2 from the left, my graph has no choice but to dive down towards -infinity. Why does my graph have to go down to -infinity? Why couldn't it go through the y-axis, pick up the y-intercept, and then go up towards +infinity? Why couldn't it do that? Why do we know it does not do that? Why can it not go, through the x-intercept and y-intercept and turn around and go up towards +infinity and become asymptotic with respect to this vertical asymptote?
Because it can't cross the horizontal
That's
axis.
right, because we did step number 5 here, and we determined there is no point where the graph crosses or touches the horizontal asymptote. It cannot cross this horizontal asymptote. So it has to go down to -infinity. It has no choice because it has to become asymptotic with respect to the vertical asymptote as x approaches 2 from the left. Okay, now here's a tricky situation. For x greater than 2, where's my graph? Is my graph below the horizontal asymptote or above? I don't know. And because of that, ladies and gentlemen, we have to choose some value greater than 2 and then find out what our function's doing. So can you give me a nice value greater than 2? Let's let x be equal to maybe like 3, okay? Take 3, substitute it back into your original rational function. which is x plus 3 over x minus 2. So I'll have 3 plus 3 over 3 minus 2. And this gives me 6 over 1, or 6. Hence, I know the point 3, 6 must be a point that lies on my graph. Because of that, ladies and gentlemen, where is my graph to the right of x equals 2? Is it below the horizontal asymptote or above? If 3, 6 must be a point on the graph. Where does it have to be? It has to be above, because 3, 6 is way up here somewhere. Well, that seals the deal then on the rest of this graph, because I know that my graph has to be asymptotic with respect to this vertical asymptote as x approaches 2 from the right. So this graph has to become asymptotic with respect to that, never crossing or touching the vertical asymptote. And as x approaches positive infinity, we go far to the right on the x-axis. This graph has got to dive down to become asymptotic with respect to the horizontal asymptote. It has no choice. And we have our graph. Do we see the analysis poured into graphing this? Okay, and all the things I found and then plotted. All right, that's the line of reasoning that you want to go through to sketch a graph of a rational function. You want to find all these things, plot them, and then if you have to find any other points, you may have to do that, okay? But we accurately have a graph of that rational function, and I did not even need a graphing calculator to graph it, okay? All right, maybe we should try another one. Suppose you want to sketch the graph of this one. This rational function, f of x is equal to 4x over x squared minus 4. So I want to try to sketch the graph of this rational function. Step number 1, is there any y-intercept? Well, to find the y-intercept, we always let x be 0. So therefore, f of 0 will be our y-intercept, should it exist. So we have 4 times 0 over 0 squared minus 4. That's going to be 0 divided by negative 4, which is 0. It does appear my y-intercept is the origin 0, 0. So it does have a y-intercept, it's the origin. Number 2, any x-intercepts. To find an x-intercept, we always let y, which is really called f of x in this case, be equal to 0. Which means I would have to set my rational function equal to 0 and then solve for x to try to identify if there's any x-intercepts. So now I got to solve this equation for x. To do that, I need to get rid of this fraction on the left side of my equation. To do that, I will multiply both sides by x squared minus 4. When I multiply the left side by x squared minus 4, the x squared minus 4's drop out, leaving me with just 4x. When I multiply the right side by x squared minus 4, I'm still left with 0. Now we have a very simple equation to solve for x. Dividing both sides by 4, we determine that x is equal to 0. So we do have an x-intercept. It also happens to be the origin. So my origin is not only a y-intercept, it's also an x-intercept. Any questions so far here? All right, now, number 3, vertical asymptotes. Are there any? VA is short for vertical asymptotes. To find them, we are concerned when our denominator becomes 0. So what I'm going to do is take this x squared minus 4, set it equal to 0, and now we're going to solve for x to determine where our vertical asymptotes hang out, where our function is undefined. Okay. So solving this equation, this quadratic equation, the easiest way, you can use the factoring method, factor this as the product of conjugate binomials, or you can use the square root method, add 4 to both sides, take the square root of both sides. Don't forget the plus or minus square root of the number side, though. We're going to have 2 x-intercepts. One is positive 2, and the other one is going to be negative 2. Those would be your x-intercepts. Excuse me, not your x-intercepts. I made the same mistake this morning, my face-to-face section. These are your vertical asymptotes, ladies and gentlemen. That's where your vertical asymptotes hang out. These are their equations right there. You got 2 vertical asymptotes for this graph. All right, any questions how we found the vertical asymptotes? Number 4, any horizontal asymptote? Any horizontal asymptote? Well, let's look at the relationship between the degrees of the polynomials. The numerator degree is 1, the denominator degree is 2. Since the denominator degree is greater than the degree of the numerator polynomial, Do you recall from that theorem in that purple box that we went over? That indicates that we will have a horizontal asymptote, and it will be the x-axis. And what's the equation of the x-axis? Y equal to what? What's the equation of the x-axis? Y equal to what?
0.
0. Yeah.
Zero.
That's your equation of your horizontal asymptote. That is the x-axis, literally. X-axis. All right, step number 5, we really should try to see if our graph will cross or touch the horizontal asymptote. To do that, we would literally set what? Y equal to 0. Wait a minute. Didn't we already do that? Didn't we already set Y equal to 0? We did back here when we were trying to find x-intercepts. Makes sense because the horizontal asymptote is the x-axis. Well, we discovered that there's one x-intercept, namely 0, 0. So yes, the graph will cross Y equals 0 at 0, 0. See step 2. It does cross the horizontal asymptote at the origin. All right, I think we're good. Let's begin to plot what we know in the XY plane and start to maybe sketch the graph of this rational function here, okay? So I will sketch the graph, and like I said, you know, feel free to use graphing paper if you want. Nothing wrong with that. Okay, so what do I know? I know that the y-intercept is 0, 0 and the x-intercept is 0, 0. So there's my only x-intercept and there's my only y-intercept. It's the origin. What else do I know? Oh, I got vertical asymptotes at x equals 2 and negative 2. Let's plot those. Take a ruler. And 1, 2, okay, negative 1, negative 2 here. All right, so I'm gonna have a vertical asymptote going right through here. Make sure it's always a dashed line. Make sure your asymptotes are always dashed lines, whether they are vertical, horizontal, or slant. There you go, right there. There's your vertical asymptotes. Did I have a horizontal asymptote? Yes, I did. Y equals 0, which is the x-axis. That is my horizontal asymptote. So you can put a dashed line that coincides with the x-axis because this is your horizontal. That is your horizontal asymptote, literally the x-axis. All right. And we know the graph crosses our horizontal asymptote at the origin 0, 0. I think we're ready to analyze this situation now. Let's go over here. Now, I have a question for you. Is my graph for values of x that are less than negative 2, is my graph going to be above the horizontal asymptote, the x-axis, or below? We don't know. And because we don't know that, ladies and gentlemen, we need to choose a value out of this interval here, which I'll call interval number 1. And we need to throw it into our function to see where our graph is. Give me some nice value for interval number 1 here. Some value less than negative 2.
Negative 4.
All right, let's put negative 4 into our function. Therefore, f of negative 4 is going to be, so what I'm doing is I'm putting negative 4 back in wherever I see x into the original rational function we've been asked to graph. Negative 4 drops in here and here, and then we'll evaluate it. So I got 4 times negative 4 over negative 4 squared minus 4. Well, what's this going to give me? Well, that's negative 16. This is going to be positive 16 minus 4 is 12. And therefore, it's going to be negative 16/12, which by 4 reduces down to negative 4/3, which is negative 1 1/3. So I have a question for you. Where is my graph in interval number 1 for values of x that are less than negative 2? Is it below or above the horizontal asymptote, the x-axis? Where will it be?
Below.
Yeah, it's negative. We got negative 1 1/3 when we plugged in negative 4. So this point, negative 4, negative 1 1/3 has to lie on the graph. So therefore, negative 4 is out here, and negative 1 1/3 you know, maybe right down here. Okay, so that kind of seals the deal on what's going on with the leftmost branch of this rational functions graph. And notice the graph is never going to cross this horizontal asymptote. We already determined the only point at which it does that is the origin way back over here. So therefore, we can easily pencil in this graph. It's going to come down like this. Then it has no choice but to turn around and drop down towards negative infinity and become asymptotic with respect to x equals -2. That's the graph of the leftmost branch. Everybody got that there? All right, we're good with that. Now we need to venture inside. We need to venture in this interval here. I'll call this interval number 2. I don't know if my graph is above or below my horizontal asymptote in this interval between 0 and -2. For that reason, I need to choose some value and throw it into the function. Give me some nice value between 0 and -2. Although you can go with a messy decimal fraction, why do that when you can choose x equals -1? Let's put -1 into our function, the original rational function. So I throw -1 in wherever I see x, and then I evaluate to see where this graph is. So I got -4 over, this is going to be 1 minus 4, which is -3. So I got 4/3, which is 1 1/3. Therefore, it must be true then that -1, 1 1/3 must lie on the graph. So therefore, since we found this point to lie on our graph on the interval from 0 to -2, my graph's going to be above the horizontal asymptote or the x-axis. So therefore, ladies and gentlemen, since it's above, it must be asymptotic with respect to the vertical asymptote x equals -2, and it must come down and grab this y-intercept or x-intercept. It has to do that on the interval from 0 to -2. Now let's go on the interval from 0 to +2. We'll call this interval maybe number 3. This little interval here, interval 3. Give me a nice value on interval 3 between 0 and 2.
1.
Just let x be 1, throw 1 into our function, and we'll have 4 times 1 over 1 squared minus 4. Hence, we're going to have 4 over -3, which, you know, is -1 and 1/3. So the point 1, -1 and 1/3 lies on our graph. So on this interval from 0 to 2, we know that 1, -1 and 1/3 lies on our graph. So we have to be down here. So therefore, okay, now we know how the graph's going to behave in this interval, because it's got to come through the x-axis and it has to be asymptotic. How do I know this graph cannot come down here and pick up this point, turn around and go back up and be asymptotic this away? How do I know it can't turn around and, you know, approach positive infinity in relation to this next vertical asymptote x equals 2? Because it cannot cross the x-axis anymore. The only point of intersection was 0, 0. That was the only point. So it cannot turn around and come back through the x-axis, the horizontal asymptote. So it has no choice but to pick up this point, 1, -1 1/3, and then dive down towards negative infinity and become asymptotic with respect to this vertical line, x equals 2, the other vertical asymptote. Finally, is our graph above or below the horizontal asymptote in this interval? We'll call interval number 4 here. To determine that, give me some value greater than 2. We'll throw it into the function and find out where it's at. So we're almost done with this. I'm going to choose x to be equal to like +4. Throw +4 into this thing. I got 4 times 4 over 4 squared minus 4. In which case I got 16 over 12. 16 over 12. I need not go any further. I know this is positive, so I know my graph on this interval where x is greater than 2 is above the horizontal asymptote, the x-axis. So therefore, my graph has to do this number. And there you go. We're done. We have sketched the graph of that rational function by going through that analysis here. Everybody understand what was poured into graphing this thing here? So that's basically how you approach graphing any rational function. You find all the attributes that we found, the y-intercept, x-intercept, vertical asymptotes, horizontal asymptotes. Does the graph cross or touch the horizontal asymptote? If it does, where? Maybe you might have a slant asymptote. You might not have a horizontal asymptote, or maybe you won't even have a horizontal asymptote or a slant asymptote. So be prepared for that. And then basically what you do is you start analyzing the graph on intervals that are basically determined by x-intercepts and also vertical asymptotes, okay? To accurately begin to put together the branches of the graph of the rational function. The only way you get good at this is by doing a lot of practice, okay? By trying to graph several of these. And I will make sure through Alex that you do get practice in doing that. All right. So we ready to close the door on this section now? A lengthy section, 3.5, rational functions. All right, let's close the door there. And now, ladies and gentlemen, I am going to begin to try to wade into section 3.6. I don't think I'll be able to finish it today, but at least I'll give it a whirl and see how much we can get done. I did not really finish it in my face-to-face section this morning either, so it doesn't surprise me here. All right, 3.6 is going to address solving what are called polynomial inequalities or rational inequalities. So that's what we're going to try to do here. Solve polynomial or rational inequalities in section 3.6. Oh, one more note about section 3.5. I want you guys to study over examples 9 and 10, also in section 3.5. Make sure you do that. So make sure you look at these examples in their entirety and study them over. The author does a pretty good job in laying all the steps out, okay? Almost to the point where I'm almost going to be put out of business here if they get any better. You guys won't need me. All right, so yeah, always try to look at the examples in this math book. Of any sections I cover, it's always wise to kind of go over the examples because it only helps you to better understand what's going on. And it gives you different looks that I may not give you in class. So it's very important. All right, so what are polynomial inequalities? Well, we're going to have some sort of a polynomial that's either going to be greater than or equal to, or could be less than, or could be less than or equal to, okay? 0. So we're going to learn how to solve polynomial inequalities. Step number 1. You want to get your inequality set to 0, okay? So you want to set the inequality to 0. That means you want to get 0 on one side. So you may have to do some algebra to accomplish that. Step number 2, then you want to completely factor the non-zero side. And this is where your factoring of polynomial skills comes back to visit you. Completely factor the non-zero side. All right. And then later on, we want to find, I think your author may refer to these as significant values. I always like to call them critical values. But critical values could be somewhat of a conflict when you get into your first semester of calculus, in which case they also use that term, critical values, to represent where you have relative extrema hanging out for the graph of a function, where your first derivative is equal to 0. But I will call them critical values. Your author might call them, I think your author might refer to them as significant values. Significant values or critical values. So you want to find these, and how do you find them? You find them by setting the variable factors that you have in step 2 after completely factoring the non-zero side. You want to set your variable factors equal to 0. And then you want to, solve the equations to find these critical or significant values. And basically you want to solve the resultant equations. Now, these critical values are going to partition up the x-axis. into disjoint intervals. And what are we going to do with these disjoint intervals here? Well, in step 4, we're going to test our polynomial inequality. So we're going to test out our polynomial inequality for each interval. And by doing that, that will enable us to ultimately put together the solution set of the polynomial inequality. So the last step is we're actually just going to form our solution set then. And that's it. Basically, those are the steps to pursue when trying to solve a polynomial inequality. Okay. And I am going to try to walk through at least one here. I think I have enough time for one. And who knows, maybe some extra change left or something, or maybe I'll have you try one. Okay. So, all right. Any questions on this here? Okay. So those are the steps that, again, you want to kind of consider when being asked to solve a polynomial inequality. Kind of walk down in this fashion here, in this order. All right. Okay. So what I'm going to do is give us one to actually solve. And we'll see how we put these steps into practice here. So here it is. Here's an example. 3x times x minus 1 is greater than 10 minus 2x. We want to solve this polynomial inequality for its solution set. And its solution set will, if it has solutions, will consist of an infinite number of real numbers, of which we are going to have to represent, usually using interval notation, or you could even use set builder notation, which is also used, but interval notation would be fine. All right, so the first thing is we got to get this thing set to 0. Well, in moving in that direction, first I'm going to distribute this 3x inside the parentheses. Notice this is not just a linear or first degree inequality. If it was, we wouldn't have to go through any of this jazz here that I laid out on this page here. We wouldn't have to go through any of this. If it was just a linear or first degree inequality, we just basically solve for x as if we're solving for an equation. But this is not a linear inequality because 3x times x is going to generate a quadratic or second degree term. So this is a quadratic inequality. 3x times negative 1 is minus 3x. 10 minus 2x. And now what we have to do is solve this quadratic or polynomial inequality. To do that, I'm going to drag my 2x over to the left side by adding 2x to both sides. And I'm also going to subtract 10 from both sides. When I do all that, my left side is going to be 3x squared, negative 3x plus 2x is plus 1x, and then I got my minus 10, and that's going to be greater than 0. Does everybody understand how I got to this point? How I got my inequality down to there?
Isn't
right.
it minus 1x?
Well, let's see here. It should be minus 1x. You know, I just bought a bottle of brand new whiteout from the dollar store, and for the life of me, it's gone. Somebody drank it. It should be a minus. You are correct. Minus 1x. My bad. All right. Now, what's the next step? Do you remember? After I get my polynomial set to 0, my inequality set to 0, what do I do next? We got to try to completely factor that left side. Do you agree? All right, so we have to factor this trinomial. And unfortunately, it's a nasty one to factor. It does not have a leading coefficient of positive 1. And of course, you'd try grouping on it. 3 times negative 10. 3 times negative 10 is negative 30. Do there exist factors of negative 30 that add up to negative 1, the middle coefficient? Is this thing even factorable? Well, 2 factors of negative 30 that add up to negative 1 would be negative 6 and 5. So it does appear to be what? Factorable, right? All right. Now, I'm not going to take the time to go through the grouping method. We've done that a million times in the past. Or if you have the trial and error method to factor these types of trinomials, you go ahead and use it. The bottom line is we have got to get this thing what? We have to get this factored. All right, that's the important thing. So after going through whatever method you want to go through, hopefully you discover that this will factor like that. All right, I factored the left side completely. What's the next step now? Non-zero side's been completely factored. The next thing is we need to find what are called critical or significant values. These are found by setting our variable factors equal to 0 and then solving the equations. In other words, I got to set 3x plus 5 equal to 0, and I got to set x minus 2 equal to 0. Solving this first equation for x by subtracting 5 from both sides of the equation, and dividing both sides by 3, we get negative 5/3 as being one of our critical or significant values here. Okay. And if you want to turn it into a mixed number for, I don't know, plotting purposes, you could, call it negative 1 2/3 here. Solving this equation for x, we get x equals 2. So these are our critical values or our significant values, as I think your author refers to them. What are these values going to do? What these values are going to do is they're going to partition up our x-axis. So therefore, we're going to place them on the x-axis. There's my x-axis. There's 0 for reference. There's negative 1 2/3 right here. And I got positive 2 over here. These critical or significant numbers or values are going to partition my number line up into 3 different intervals. Interval number 1, interval number 2, and interval number 3. All that remains now is testing out each of these 3 intervals with our polynomial inequality up here to see which interval or intervals yield solutions to this inequality. All right, interval number 1, can you give me a nice value for x that's less than negative 1 2/3? What value you want to go with? Less than negative 1 2/3. Now you could choose negative 1 million, but why do that? Why not just choose maybe like negative 4 or something? Put negative 4 into your polynomial inequality. Notice I'm going to put it into the factored form, not the non-factored form. It's just easier to deal with here. So I'm going to put negative 4 in for x here into this factor. And then I'm going to put negative 4 into this factor here. And I'm going to ask myself, is this greater than 0? This is negative 12, and negative 12 plus 5 is negative 7. This is going to be, what is this going to be? Negative 6? Negative 7 times negative 6 is what? Positive 42, is that correct? Is 42 greater than 0? That is true. What I like to do is just write the word true in this interval. The word true means that, yes, solutions for this inequality will be coming from this interval. Any number that's less than negative 1 2/3 will be a solution to this polynomial or quadratic inequality. Interval number 2, now we need to test out. Give me a nice value between negative 1 2/3 and 2. What is the nicest value you could possibly choose in this interval?
Negative 1.
Oh, we go even better than negative 1. How about this one? What's that guy? 0. How about 0? How about just 0? 0 is even funner to work with, isn't it? The reason why 0 is so fun to work with, ladies and gentlemen, is because whenever you multiply anything by 0, it's gone. So this is going to be 5 times negative 2, which is negative 10. Is negative 10 greater than 0? Is this true? When I put 0 in here and here, is the left side greater than 0? Is negative 10 greater than 0? That's false. So no solutions will be coming from this middle interval. Dead zone. No solutions are going to be chosen for this inequality out of this interval. Give me something nice greater than 2. Anything.
4.
All right. Let's let x be 4. take 4, substitute it back in here for x, and then verify. Is the left side greater than 0? Is 4 a solution to this quadratic inequality? Well, there goes 4 in there, and here goes 4 in here. And then we got to evaluate this. This is going to be 12 plus 5, which is what, 17? And this is 4 minus 2, which is 2. 17 times 2 is 34. Is 34 greater than 0? Is that true? That's true all day long. And so, yes, solutions will be coming from this interval. We're ready to put together our solution set now. I have a question for you. Will actually negative 1 2/3 and 2 actually be in the solution set? Will x equal to negative 1 1/3 and x equal to 2 be in the solution set? How do we know? Well, you could plug them in and find out if they work, but why do we not even have to do that? What kind of an inequality do I have here? Do I have my equal sign as part of this inequality? No, there is no equal sign. This is a strict inequality. Because I don't have the equal sign as part of my inequality, then these critical values or significant values will not be in the solution set. Therefore, do not include them. If I had greater than or equal to, if I had equal sign as part of this, yes, these then would both be in the solution set, but they're not. So I have a parenthesis and I shade to the left. Then I have an open parenthesis on 2, shade to the right. You're looking at the graph of the solution set of this quadratic inequality or this polynomial inequality. As long as you choose a real number from this interval or this interval, it will be a solution to this inequality. You choose something in between, or like if you actually choose these critical values, they will not be solutions. So how would we put the solution set together? Using interval notation, working from left to right. We're coming from negative infinity up to negative 1 2/3 or negative 5/3. You can go back to negative 5/3, not including negative 5/3, in union with not including 2 up to positive infinity. This would be your solution set for that polynomial inequality. Everybody understand how I just solved that polynomial inequality? Everybody understand how we solved that there? Okay. See that there? All right.
Can you show the solution set, please?
Yeah, solution set's right here.
Thank you.
There's the graph or there's interval notation there. All right. All right, you guys want to try one as the last classwork today? This will be the last problem we work on. We'll call this classwork number, well, just call it the last classwork, okay? I'm going to give you one, and I want to see if you can solve this polynomial inequality, right? Any other questions about this last one here? All right, here we go. We'll call it the last classwork. I want you to solve this polynomial inequality. Why is this polynomial inequality so nice? Why is it so nice to work with?
30 factor.
It's already completely factored and we got it set to 0. You're good to go. You're good to find the critical values or the significant values and start testing your intervals. Go ahead, find the solution set for that inequality. Pretty easy problem. All righty. Hopefully, you had similar success here. The good news is the left side's already factored for us, so it's very easy to find your critical values or significant values. They are going to be -4, 1, and 3. Those numbers partition our number line up into 4 different intervals that really should be tested out with your. This would really be a 3rd degree polynomial inequality, 3rd degree if you were to expand it out. Interval number 1, I chose -5. -5, when you put it in for x here, here, and here, does not work out. It does not provide a solution to this inequality. I chose some value between -4 and 1, which I chose 0 in interval number 2, of which we do get a solution to our inequality. Choosing between 1 and 3, I chose 2. That does not work out. And choosing some value greater than 3, I chose 4. It does work out as a solution. And basically, now why do I include the significant values or the critical values? I do include those in my solution set because we have the equal sign. You see, because we got the equal sign. So if you actually put 4 in, -4 in, this factor goes to 0, and the whole thing zeroes out on the left side. And 0 is not greater than itself, but it is equal to 0. 0 is equal to itself. That's why you must include -4. You put 1 in, this factor becomes 0, and the whole left side becomes 0, and 0 is equal to itself. Or you put 3 in, this factor becomes 0, and the whole thing becomes 0 on the left side. That's why you must include those critical values or significant values. Did anybody get that for your solution set? And this is interval notation there.
Yeah.
All right, great. I think that's about all we have time for. There will be more problems that I'm going to have to do out of section 3.6. I'm going to have to show you maybe a couple more of these polynomial inequalities and also show you how to solve some rational inequalities. And then we'll wrap it up for 3.6. But I'll have to probably do that next time. I just don't have enough time right now. All right, ladies and gentlemen, that is it for today. If you have any questions,